So this last lesson in fluids is going to be about Bernoulli's equation, which is the equation that really encompasses everything all together. Fundamentally, its work is the change in energy, but it allows us to handle dynamic fluids and even static fluids if you make the velocity zero. So it is a nice general equation that can be used for any scenario, but more commonly used when fluids are moving. So now let's look at Bernoulli's equation. And Bernoulli's equation, again, is handling fluid dynamics. Water is flowing through a pipe. And this equation is actually not very complicated. It's actually a form of work and energy. And I'm just going to illustrate to you why. It's not that insightful to see, but it's basically work is a change in energy. The pressure is from the work. If I move the P1 minus P2 to this side, or you could, P1 to, and then move this part over to here, you get this rho g h2 plus 1/2 rho v2 squared, and then I'm going to put a minus all of this stuff, rho g h1 plus 1/2 rho v1 squared, right? And if I then multiply or times by the area, because remember density is mass divided by the volume. So if I multiply by, say, the volume here, the volume of the water that we're moving, okay? Then when I multiply by the volumes, all of these densities become masses, right? mgh2 plus 1/2 mv2 squared, right? Minus mgh1 plus 1/2 mv1 squared, because that's the density of the water. And then this pressure has to do with the fact that the water is moving from one point to another. So the pressure down here, this is P1, and the pressure up here, if you imagine this like cylinder of water that we're lifting up, or water is flowing here, right? Then what we're talking about is there's this difference in the pressure. If I'm lifting it up, is a force, right? So if you multiply by the volume, think of the volume as like the area here times this delta x, right? So then you do P1 minus P2, right, times the area times delta x. That's the volume there. Pressure times area is going to be this force. So this is going to be the external force times delta x, and that's going to be work, right? Because the pressure times the area is going to be this external force here, and that's going to be the work. So, and then this is the energy at the top. This is the energy at the bottom as the water is moving. So its work is the change in energy, okay? So that's where it comes from. It's a work-energy theorem. You can derive it from work and energy from some principles. I won't go into that necessarily now, but you certainly could, and it's all simply an application of Unit 3, okay? But with density in fluids. Let's go through the problem. The more practical side is, what are the problem-solving steps? How do we use a Bernoulli's equation? So we're going to identify 2 points of interest within the system. That's going to be 1 and 2. We want to determine the pressure at both points. Whenever the fluid is exposed to the air, the pressure will be 1 atmosphere. So that's a key tip. And do not use this part when the fluid is moving. Actually, if it turns out you can't use this, because this is for static pressure. Actually, that equation will come out is, if we assume the fluid isn't moving, if we zero these terms out because it's not moving, what you're going to get is you're going to get that hydrostatic pressure equation. You're just going to have H2 minus H1, which is the height difference. So we cannot use this equation. This equation is a simplification. Like Bernoulli's equation reduces to this form, okay, when you're using, when the velocity is not zero. So we can't use that to find the pressure. Has to be either given to us or exposed to the air, which is the most common scenario, where we know would be 10 to the 5th pascals. We want to determine the velocity at both points, and you might need to use continuity equation to do this. So either we're going to do this and get an expression for it, or we need to calculate it. We want to set a reference height, because remember that height there is based on gravitational potential energy. So we're going to want to set a reference height of h is equal to 0. Again, like we do in energy, when we're doing gravitational potential energy, I usually make h equals 0 the lower point of the 2 points we're interested in, and then we fill in the values for Bernoulli's equation. Okay, so that's how we're going to handle any Bernoulli's equation problem. This is generally pretty straightforward for here. So water is being pumped from a well up to a house. The bottom of the well is 30 meters below the house. So we have a house here. I'll draw a nice picture here. And we have some water here down here from a pipe, and we'll say that that is 30 meters. The intake pipe, that is the pipe here, has a radius of 0.25 meters. If we want the water in the house to come out of a faucet, so the water is going to come out of a faucet. It's going to come into here, come out of a little pipe of faucet, which has a radius of 0.05 meters. And we want the water to come out at 5 meters per second here. So then we want to know how much pressure must be exerted at the bottom of the well. Okay, so this is our point. This is our bottom point. We'll call this point 1 down here. And here is point 2. Okay, and so then we're going to look at, I just write out the equation and I just start filling in the things that we know a little bit. Okay, so we say P1 plus rho G H1 plus 1/2 rho V1 squared is equal to P2 plus rho G H2 plus 1/2 rho V2 squared, right? This is our Bernoulli's equation. We're going to set a reference height. So I'm going to set down here as H equal to 0. So this part is going to be 0 for this guy. We know V2. V2 is going to be the, 5 meters per second. So we know that quantity here. We know the height that we want to go up. This is 30 meters, right? We know G. The pressure, do we know the pressures here? Well, this is exposed to the air. It's a faucet. I'm going to turn it on. Water's going to come out into the air. This is going to be 10 to the 5th pascals, right? Now, I want to figure out, this is what I want to figure out, right? So I need to know this guy right here. I need to know how fast the water is going to go. And that's where we're going to use continuity equation to find that, right? Because I know how much water is coming out. So we're going to use A₁v₁ is equal to A₂v₂. This is going to be pi times 0.25 squared times V1 is equal to A2, which is pi times 0.05 squared times V2, which is 5. So we can solve for V1 here. Okay, the pi's cancel. So let's see, when it's going to be, I'll just do the math on my calculator instead of trying to do it in my head. It's going to be 0.2 meters per second. So now we know that this is 0.2. Water density, I wasn't given in the problem, but water density is about 1,000 kilograms per cubic meters. So then you can solve for the P1 now. So P1 plus 1/2 times 1,000 times 0.2 is equal to 10 to the 5th plus 1,000. We'll use G of 10 times 30 plus 1/2 times 1,000 times 5 squared. Okay, and then we just solve for P1. So this is 1E5 plus 1,000 times 10 times 30 times 5 squared, then minus 0.5 times 1,000 times 0.2. Oh, this should be a squared here. And so I get 4.12 times 10 to the 5th pascals. Okay, so pretty straightforward on using that. Let's look at another problem here. So we have two students. This is an old FRQ. Students observe a water flowing to the left or the right through a section of the pipe shown, which decreases in diameter, increases in elevation. The pipe ends on the right where the water exits vertically. Point A, the water is known to have a speed of 0.5 meters per second and a pressure of 2 times 10 to the 5th pascal. The density of water is 1,000. Okay, so they know the pressure and the speed here, which is good. Right, we'll call that VA, and we know the pressure there. Calculate the following at point B, the speed and pressure at that point there. Okay, so how are we going to handle that? Right, so again, fluid, water is moving. There's only two equations we use, continuity equation, Bernoulli's. I always start with Bernoulli's because that's going to give us the most general. So instead of 1 and 2, we'll just call it A and B. Same thing though, rho GHA plus 1/2 rho VA squared is going to equal, let me scroll up a little bit. Pressure at B plus rho GHB plus 1/2 rho VB squared. Okay, so we know some of these quantities. For example, let's set our reference height. So we'll make this H equals 0. So we know that this guy will be 0. We know at this point, we know the VA is 0.5. We want to know this guy. And we want to know this guy right here. So we have two unknowns. So that means we're going to have to do something else. The HB here we know is from there to there is... Oh, actually, we want to know the speed of the water at point B. Yeah, so that's 5 meters. I was thinking whether should I include that 1 meter, but we're doing it to point B. That's our point there. Right, and so how do we need to solve for this guy, I need to know this guy. So that's why the first thing they ask us to do... Oh, the pressure at A, we know this. This is 2 times 10 to the 5th. Okay, so we need to know what the velocity at B is, and that's where we're going to use continuity equation, because the amount of water flowing in here has to equal the amount of flowing out, because again, water is incompressible. So the area at A times the velocity at A has to be the area at B times the velocity at B as well. So this is going to be pi times the diameter is 2.5 centimeters. That is 0.025 meters, but the radius is half of that. So 0.025 divided by 2 squared times the velocity, which is 0.5, has to equal the area at this point, which is pi times 0.015 divided by 2 squared times the velocity at B. So we can find the velocity at B by just looking at that equation. So we're going to say 0.5 times 0.25 squared is going to be 1.39 meters per second. Okay, and then from there, because that's 1.39, I can then solve for the pressure at B, because I have everything else. I know rho is 1,000 and things like that. So we can solve for the pressure at B using that equation. We're going to do this quantity and subtract all of this stuff over here. So it's going to be 2 times 10 to the 5 plus 0.5 times 1,000 times 0.5 squared minus 1,000 times 10. I'm going to use g of 10 when I do this calculation. Minus 0.5 times 1,000 times this number squared. And I get 1.49 times 10 to the 5th pascals. Okay. A valve to the left now closes off the end of the pipe. The section of the pipe is still full of water, but no water is no longer flowing. So now we're static. Water is not flowing anymore. So we're in static fluids now. Calculate the absolute pressure at point A. The pressure includes the effect of the atmosphere. So you can still use Bernoulli's, but now all the velocities are 0 here. So you can say, all right, well, we know the pressure, we know here is atmospheric pressure, which is 10 to the 5th, right, at here. And then we just want to know the pressure at A is just going to be that vertical distance, P0 plus rho GH. Now, be very careful here. We want the distance from the opening here, which is 6 meters, right? So this is 100,000 plus 60,000, so it's going to be 160,000 pascals, like that. Okay, thanks for watching. Please subscribe if you haven't already, just to like improve the quality of the channel, so it shows up more, so we can share this out with more and more students out there. The other thing is if you do need extra help, if you're needing maybe some more practice questions, more guidance on multiple choice questions, we do have program options to help you practice. Also run office hours. I answer questions for students, things like that. A little bit more just structured guidance. If you feel like you're needing some of that, go ahead and click the description below. There will be a link that takes you to a website where you can see about how the different programs operate for all the AP Physics and AP Calculus programs we run.